When you need to count a lot of things quickly, counting them one by one is a terrible strategy. So we've developed a habit of grouping things into mental shortcuts. If you buy shoes, you don't ask for two individual units, you ask for a pair. If you're picking up eggs, you don't count out 12, you just grab a dozen. The specific word we choose depends entirely on what we're counting. A pair works for shoes, but you'd never use it to describe the grains in a bag of rice. This is the problem chemists face every day. They work with atoms, the tiny building blocks that make up absolutely everything in our world. These blocks are so small that a single drop of water contains more individual atoms than there are stars in the observable night sky. At this scale, human words like dozen or even billion stop being useful. Trying to count atoms with them is like trying to empty the ocean with a teaspoon. To make the math of the universe possible, scientists needed a new grouping word, one that could handle the sheer volume of the microscopic world. That specific word is called the mole. Just as a dozen means 12, a mole always means exactly 6.022 times 10 to the 23rd power. If you had a mole of donuts, they would cover the entire surface of the Earth in a layer several miles deep. This specific quantity is known as Avogadro's number. It's named after Amedeo Avogadro, an Italian researcher who helped lay the groundwork for how we understand molecules today. Despite its size, it functions like any other unit. Half a mole is simply half of that total count, just as half a dozen is 6. But why use such a complex, specific number? It seems like an unnecessarily difficult choice for a standard measurement. The reason is found in how we weigh atoms. Because they are too small for normal scales, we use microscopic units called atomic mass units, or AMU. We use the carbon atom as our benchmark. One single atom of carbon is defined as weighing exactly 12 of these microscopic units. The problem is that no tool in a human-sized laboratory is sensitive enough to measure something that small. In our world, we measure weight in grams. To bridge these two worlds, scientists defined the mole using that same carbon benchmark. They calculated exactly how many atoms it would take to turn that microscopic 12 into a human-scale 12 grams. When you gather 1 mole of carbon atoms, the total weight on a laboratory scale becomes exactly 12 grams. Because both systems are anchored to the same carbon atom, the numbers now match for every element. An atom's microscopic weight will always be the same as the weight of 1 mole in grams. This allows scientists to switch between the world of individual atoms and the world of laboratory samples without needing to do any complex conversions. Avogadro's number is the mathematical glue that connects the invisible weight of a single atom to the tangible weight we can measure on a scale. This triangle shows the workflow chemists use. To find how many moles are inside a sample, divide your total grams by the element's grams per mole weight. From there, find the exact number of particles by multiplying those moles by Avogadro's number. Chemistry math isn't a collection of random formulas. It's a system of groupings that allows us to handle the universe's smallest building blocks using the tools we already have.